Welcome to our series on trigonometry. Here are 4 questions based on Pythagorean identities. All of them have higher orders. Let us see how to solve such questions. In case you want to learn from me, you can always send an email on the address given. Enjoy the journey of success and learn. Let us now see how do we solve such questions. I am Anil Kumar. Welcome to my YouTube channel and the website Global Math Institute. In this video, we'll discuss trigonometric identities with higher degree. Here are 4 questions. You can pause the video, answer these questions, and then look into my suggestions. In case you want to learn from me, you can send an email on the address given. You need to prove the following trigonometric identities. Question number 1. Sine cube x cos to the power of 4x equals to cos to the power of 4x minus cos to the power of 6x times sine x. Tan 4x equals to tan square x secant square x minus tan square x. Cosecant to the power of 4x cotangent x equals to cosecant to the power of 4x times, within brackets, cot x plus cot cube x. Cos to the power of 4x minus cos square x equals to sine to the power of 4x minus sine square x. These are 4 questions. We'll see what strategy to follow to answer these questions. Well, in all of them, we are going to use the Pythagorean identities, which you know are sine square theta plus cos square theta equals to 1, 1 plus tan square theta equals to secant square theta, and 1 plus cotangent square theta is cosecant square theta, correct? Now these Pythagorean identities can be rearranged and then utilized to prove the above identities. I'd like you to now pause the video, answer the question, and then look into my suggestions. Let us take the first one now. Sine cube x cos to the power of 4x is equal to cos to the power of 4x minus cos to the power of 6x sine x. So what do we notice? We notice one thing, that cosine powers are increasing, correct? So the strategy is that the cosine powers are increasing and the cos sine power is decreasing. So that means we should replace sine square x with 1 minus cos square x. That should help, right? Sine cube is given to us. We can split this into sine x and sine square x, do the replacement, and then get the answer. Does that sound good? Exactly. This is what we are going to do, right? So let's rewrite this question. We have sine cube x times cos of 4x. That is the left hand side. We can split sine cube x and write this as sine x times sine square x times cos of 4x. Since the power of 4 is power of cos is 4, lowest, right? So that works. So now we can expand this, keeping sine x, which is required. So we'll just maintain this, and then we'll expand sine square x. So we have sine x within brackets 1 minus cos square x times cos to the power of 4x. Now if you distribute, you get the right hand side, as you can see, right? So we have sine x times cos to the power of 4x minus cos to the power of 6x. You see how simple it is? That is how you could do it. Correct? So here is the solution for you. Basically, we use this strategy of Pythagorean identity sin square x plus cos square x equals to 1, written as sin square x equals to 1 minus cos square x. Correct? So that is what we did after splitting sin cube as product of sin square and sin x. And then by distributive property, we got our result. Make sense? Now let's look into the second question, where we have tan to the power of 4x. And we have to write as tan square x secant square x minus tan square x. Well, tan square x is common. That do suggest us something, right? So let's begin with the left hand side. As we did earlier, we have tan to the power of 4x. We'll write this as tan square x times tan square x. Since we want to retain tan square x, we'll keep this as such, but expand tan square x as what? Well, the identity is, let me write down here, 1 plus tan square x equals to secant square x. And therefore, tan square x can be written as secant square x minus 1. So that is what we are going to write here. So tan square x as secant square x minus 1, and we already have tan square x outside. Now if you distribute, you get your result, which is tan square x secant square x minus tan square x. Perfect. So we got this one also. Now let's look into the questions. We have done question 1 and 2. I will leave question number 3 for you to practice. Strategy is similar, right? So that becomes your practice question. You can try this as your test question. Question number 4. Okay, so you can pause and try it as a test question. Here is our short solution to this same question. Now in this particular case, you see that all the cosine terms have been written in terms of sine. So let's see, how do we do that? Well, let's begin with cos to the power of 4x, which is the left hand side, right? So let me begin with the left hand side, which is cos 4x minus cos square x. We can take cos square x common, right? And we get cos square x minus 1. Now, cos square x can be written as 1 minus sine square x. So we will get cos to the power of 4. Correct? So that could be one of our strategy. Now, cos square x minus 1 can also be written as sine, right? So let's look into what we have. We know that sine square x plus cos square x equals to 1. So, cos square x minus 1 will be equal to what? Minus sine square x, correct? That is one thing. And we could write cos square x as equal to 1 minus sine square x. So we can do both these substitutions here. So cos square x can be written as 1 minus sine square x, and cos square x minus 1 can be written as minus sine square x. Now if we expand, what do we get? We get minus sine square x plus sine to the power of 4x. Rearranging, we get this as equal to sine to the power of 4x minus sine square x. Perfect. Which is the same as right hand side. You see how we can actually solve or prove these identities. Perfect. I hope you understand and appreciate it. In case you want to learn from me, you can send an email on this address. Thanks for your time and all the best.